Welcome and hello. This is a video lesson in PyDSSTools titled Paired Data Reading. What we're going to be doing is reading a paired data set from our data.dss file and then extracting those data values and the metadata into Python where we can use that. What we see on the screen here is a plot. This happens to be a pump curve. So we have head versus flow rate. On the X and Y axis, we can access those data values by selecting that particular path and then clicking on the tabulate button. So for the different heads, we have different flow rates for three different powers: 50 horsepower, 100 horsepower, and 200 horsepower. Right, so we're going to get started with extracting this data, not only the data values themselves, but also the metadata. So to do that, I'm going to head over to my coding environment. This is Visual Studio Community Edition. That's what I downloaded and installed. That's covered in lesson 1 of this playlist if you're just getting started. We'll also leave a link to the documentation, which is this page right here. This is the documentation for PyDSSTools for reading data from a paired data set. We can find that under topics over here on the left, and then click on paired data. Then what we have here is a little bit of an introduction first. This guide covers reading, writing, and managing paired data records in HEC-DSS files using PyDSSTools. Paired data records store tabular relationships between independent variables, x-axis, and dependent variables, which are on the y-axis. So some examples of that would be, like I said, the pump curve, which is what we're going to be using. There's also stage discharge curves, rating curves, which is common for like a river reach, elevation storage curves, which is common for volume curves for a reservoir. So paired data is used and comes up all the time in water resources engineering and the HEC water modeling programs. Further down, we have some key concepts. So paired data is the X and Y values. Paired data containers, this is an object used for writing new paired data records. We are actually dealing with reading data, so we're going to be working with a paired data struct. That's the read side structure. There's also a curve. This refers to a single column of Y values or dependent values. There are labels, shapes, windows, and real allocation records. By the way, this table right here does scroll over to the right if you're not seeing all the text. Here is an example right here, but what we also saw was an example already from my DSSVue right here. So we have independent heads and then dependent flow rates based on the head and the particular post. So we're going to be working through some of these examples. That's what inspired this video. So let's go ahead and get started. Here is my Python code. This is my script.py file. What I've pasted in here is that example 1. What we're doing is importing the HEC-DSS class. This allows us to open up the DSS file and use a file handler alias FID. We're going to be reading in the data frame. That's what read underscore TD. The DSS file is data.dss. That's just what it happened to be naming that file, which is located in the same directory as my script.py file. And then here is the particular path. I also have a path right here for all of the data. So this first path is only the 50 horsepower curve data, which is this one right here. If I open up the table data, boom, we see the flow rates for 50 horsepower. The one we were looking at previously is for all 3 pump powers right here. So let's go ahead and give this a shot. We're going to be printing out the entire data frame, and then after that, printing out the index values and the column labels. So I'm going to save that and then head over to my terminal window and then run that script, right? So what we have here is our table of values. Before I look at this, I'm going to silence some of these system notes. So you can do the same thing here as well. I'm going to just paste in this right here, lines 3, 4, and 5. And then let me go ahead and try running that again. So clear and run, right? There we go. This right here is only the 50 horsepower flow data. I'll go ahead and demonstrate the all 3 different pumps in just a moment, but 50 horsepower data is going to give us that one curve. So X values, the X data, this refers to our head, 10 feet, 20 feet, 30 feet, all the way up to 70 feet. And then the flow rates right here for our one and only curve Y0 starts at 2,000 gallons per minute, and then it slowly decreases as the head increases. Down below, we have the index values. That refers to the independent variable, the head of 10 feet up to 70 feet. And then column labels, I just don't have anything labeled here. So let's go ahead and switch the path so that we are now accessing the first path we were looking at with all three of our pumps. So say we should have three curves this time. I'm going to clear the record and then run it once again. All right, cool. So now we do have some column labels. It's important because we have three separate curves, Y0, Y1, and Y2. It looks like the labels printed out here as well. So 50 horsepower, 100 horsepower, and 200 horsepower. For the X values, we have the exact same head values from 10 up to 70 feet. And then we have three different columns here of data representing the flow rates for our three different pumps. The next example in the documentation is example 2. It talks about using a window parameter to capture only a subset of the entire data. So what we're seeing right here is the entire data. But if we wanted to limit that based on specific row or column restrictions, we can add a new parameter in the read underscore PD function. Right now, we're just reading in the path name. What we can do instead is use this window attribute, which they're using in an example right here and right here and right here. What you want to do, it is a for tuple of zero-based inclusive indices. So the first value is the row start. The second value is the row end. This is zero based, so it's going to start at 0, and then column start and column end. So if we go back to our output, which we have on the screen right here, this would be our results for row 0, row 1, row 2, row 3, 4, 5, and row 6. And then for the column values, this would be column 0, row 0, column 1, and column 2. So if we wanted to get just the first 4 rows of data, like this right here, with no restriction on the column, we want all the columns, but only the first 4 rows, we would set a start row index of 0, and then a max row index right here of 3. So 0, 1, 2, and 3. And then for the column, it would be from 0 to infinity, or what is labeled as none. So let's go ahead and just demonstrate that. We're just going to be truncating and only extracting the first 4 rows. So back here to the line 12, I'm going to add in a second parameter. What I just pasted in here is this comma space window 0, comma 3, comma 0, comma 9. So remember, we're going from index 0 through 3. It's inclusive on the rows, no restriction on the columns. I'm going to save that, then come back over to my terminal window, run once again. And now what you see is just pertaining to 10 feet through 40 feet. It doesn't go up to 70 feet as before. As a second example, let's go ahead and restrict the columns. In fact, let's print out all the rows, but only for this 100 horsepower flow rate, which would be column ID 1. So this would be column 0, column 1, and column 2. I didn't really highlight that too well, but I'm just going to update my parameters. So it's going to be 0 to none on the rows and then 1 to 1 on the columns. Go ahead and run that. So clear and run. Boom. Now we have only the data for our 100 horsepower curve. And if we wanted to extract one single row, like 2850, for instance, that would be row 0, 1, 2, and 3. So I would just come back here and instead of 0 to none, I would say 3 to 3 and save. And then let's clear and run. So this should give us a table with only one value, 2850. That is right there. One last thing to mention with regard to the window parameter is that negative indice values are supported. So if we wanted to reference, say, for instance, the last row of all 3 curves, what that would look like is a -1 here for the start row, and then none, and then 0 and none. So we're going to capture all of the curves, all of the columns, but only the last row. So -1 to the end, right? Save that, and then let's just demonstrate that in action, right? So what we see here is only the last row of data is printed out. That is a head of 70 feet. Next one I'm going to demonstrate is grabbing the individual data values and then looping through and printing those out using a struct. It's called the paired data struct, and I need to add a different parameter to the read underscore td function, which is right here. Instead of window, what I'm going to be pasting in instead here is data frame equals false. Okay? And that's going to be a paired data struct. So I'm just going to call it PDS instead. In fact, I can print out the metadata as well. So we'll do the metadata first, and then after that, we'll print out the actual values, the X and Y values. What I've pasted in here is the metadata, referencing that paired data struct. So we have the shape, the X and Y units, the type, which is really the scale that's used. That'll be linear, and then the labels. All right, so I'm going to save that and run it. Again, we're using the path for all three of the pumps here, just for a little bit more variability in the data. I'm going to clear that and then run. All right, so this, again, like I said, is sort of the metadata. We're not actually looking at the head values and the flow rate values quite yet. That's coming up next. But you can see that the shape refers to 7 rows and 3 columns of data. We have our units of feet and gallons per minute, and then the scale is linear and linear, and then here are the labels for the 3 different curves. All right, back to the script.py file. I'm going to remove the metadata and then paste in what I have prepared here to extract the individual values. What we're doing here is getting a list of the different head values. After that, we're going to be looping through all of the curves one at a time. So first it'll be the 50 horsepower, then 100 horsepower, then 200 horsepower data. I'm going to be printing out that particular label at the top of a table. Then I'm going to loop through the different head values, printing out the head value and the flow rate for that specific curve, which happens to be a pump. All right, so I'm going to save that. This should give us the actual values now. So run it. Boom. All right, let me scroll to the top. First, we have our 50 horsepower pump. I didn't have to print out all these labels, so I'm just being a little bit more explicit and verbose than necessary. But we have a head from 10 feet all the way up to 70 feet and a flow rate decreasing from 2,000 gallons per minute down to 0 gallons per minute. That was the 50 horsepower pump. Again, this is a loop instead of a loop. So we have the same table for the 100 horsepower pump. And finally, down here at the bottom, the 200 horsepower pump. And the last example in this lesson is how to get paired data info without accessing the values directly. We've seen something like this already before. I'm just going to paste in what I have prepared. In fact, we don't even need this read underscore td path anymore. What we're going to be using is this td underscore info method, and then we set the path name. It's going to be getting us some metadata, such as the number of curves, the number of points on each curve, the label size, and then down here will be the individual labels, which should print out 50 horsepower, 100 horsepower, and 200 horsepower. All right, so let's give that a shot, and boom, here is the metadata. 3 curves, 7 points per curve, so this would be like the number of columns, the number of rows, and then we have the different labels here for our 3 different pumps. All right, well, that's it for this lesson where we talked about paired data, specifically reading paired data from an existing paired data set saved in our data.dss file.